afternoon, good evening. We have people from all around the globe today. Really excited about this, and hopefully it'll be informational and hopefully some entertaining part as well. Whenever we do this February webinars, I like to start by giving some credit and tribute to the person uh, under whose name we have the unit of frequency, hertz. Heinrich Hertz was his birthday is coming up in a few days, so early happy birthday to him. He was a fascinating scientist, accomplished a lot in his short life on Earth of 36 years. He's the one. I mean, we remember him because of his the unit of frequency, but his name to fame, he definitely started by, he was the one who proved the existence of radio waves. He was the one who got this thing started, and frankly, all the wireless devices and the field of quantum computing can thank him for his pioneering research in the late 19th century. So a fascinating personality. Definitely read up on him if you get a chance. I also read somewhere that he's he was a he was a fantastic scientist, but a terrible singer. Apparently, his music teacher had to ask him to not show up for his singing lessons at one point. So that was an interesting tidbit while learn more about this about Heinrich Hertz. So, but I digress. Today's topic is all about non-contact vibration measurements. We'll go through some introduction slides, a couple of slides on Polytec, and then why do this? Who cares about vibration measurements? Instead of jumping into what is vibrometry, we like to start with showing some examples of what one can do with a vibrometer. And I hope with those examples, those are not super exotic examples, but those examples are chosen to bring out some aspect of vibrometry. So that's the goal. And then we go into vibrometries and types of vibrometer. So Polytech, just a couple of slides. We definitely pride ourselves in considering an educator, technology expert, and that um, goes beyond vibrometry with the experience we have, and with a broad spectrum of partners and integrators that we work with. We definitely consider ourselves more of a facilitator. Sometimes vibrometry is not the right thing, and at least with our expertise, we can point you in the right direction. So that's how we try to position ourselves. Polytech is all over the globe, based in Waldbronn, Germany, the manufacturing headquarters, which is about 100 kilometers or so south of Frankfurt. By the way, Heinrich Hertz was married at the age of 29 in Karlsruhe, which is a stone's throw away from Waldbronn. So we definitely have a personal connection with Heinrich Hertz. And then, yeah, we are, as this slide shows you some of the other locations where we have our offices, and we have distributors, many more distributors all around the globe. So that's Polytech. Before we get into some examples, wanted to point out, and many of you know already because I see the list of attendees. If you ever, especially for educational institutions, we have PolyLab and PolyLab Plus programs that give you access for education purposes to our vibrometers. If you don't know or would like to find out more, definitely reach out. We are very proud of this program. It's been going on for almost a decade now, and very well received. And the main goal is to educate the next generation. That's our goal with this PolyLab program. What are we going to be talking about today? It's all about measuring vibrations without contact, non-contact web measurements of vibrations. There are a couple of prerequisites. Got to stay awake and definitely, hopefully, uh, I do a decent enough job that you stay awake as well. So that's the very, very simple prerequisites for today. when it comes to vibrations, I mean, they are everywhere around us. Everything moves from the tympanic membrane or the middle ear, or the eardrum in your ear, to a washing machine, to musical instruments, to buildings and bridges, and the supercomputer that we carry in our pocket these days has all kinds of sensors as well. So, just wanted to show you the different things that go on when it comes to vibrations. Vibrations are everywhere, and some are good, some are not, and sensors come into picture when we are trying to figure out what is good and what's not. What do we do with this? So why do people measure vibrations? And again, the motivations could be several different reasons why someone would do it. One of the most common ones, let me see if I can make a laser pointer. Fe to experimental correlation is definitely high up there. When you have a numerical model, you want to validate your model. Defect detection is a big one. Some of the more exotic ones would be photoacoustics, refractive vibrometry. Modal analysis forms the foundation of many of the applications. So these are some of the, I guess, means to an end. Ultimately, it's about creating something that's better, higher performing, to improve the quality of life or a quality of a product. That's what all these take us there. What are the fundamental components of a vibration test? So obviously we start with the test article, whatever that is. So now we need something to excite this test article. This could be external excitation, like a hammer, piezo, even some non-contact excitation methods, or it could be self-excited. So like a wind exciting a wind turbine, or a running engine, or what's called Brownian motion, thermal excitation. So that's the excitation. There's a test article, there's excitation, some way to measure this vibration. That comes the sensor part, which is going to be the center stage for us to talk about these. There are some contact transducers, there are some optical methods, can be broken down into camera based, or what our focus is laser vibrometry today. So we got the excitation, we got the detection, and then we need some way to store and process and analyze the data. This is an FFT analyzer, oscilloscope. This could be something standard off the shelf, or something one may build using a lab view like framework, for example, with some custom hardware. So these are the main components: excitation, detection, data acquisition. Our focus is going to be on the detection side today. Um, when it comes to sensor selection, these are some of the questions you want to start off with, and that'll kind of help you determine what sensor is best for your application. Application is absolutely first and foremost. What is my application? What do I need? Do I need velocity, displacement, acceleration? What's my frequency range? What kind of vibration am I after? Is it linear? Is it rotational? What's the structure? Is it very lightweight? Is it solid? Is it, how far is it? So all these questions, as you answer these questions, it'll help you determine what is the right sensor, what is the best, most cost effective way to achieve the goal of this vibration measurement. So that's how we kind of try to approach it when it comes to sensor selection. So these are some of the basic questions you want to keep in mind. Now, as I said, now we'll get into the next section of the presentation, where we just start off by looking at some of the, some kind of measurements. What does one get out of a vibrometer? What kind of measurements does a vibrometer give? I like to start with this one. This was done at a museum in Chicago. This is the famous Sue the T-Rex, where they were trying to sort of quantify the effect of vibrations from outside, from some, let's say, if there's a music concert or there is some construction work going outside, what happens inside. Now, this is a classic example where, something non-contact is the way to go, because You don't want to be able to, mount any kind of contact transducer to literally one of a kind structure in this case. And here you see a couple of different vibrometers being used that we were using to measure. So the excitation was using some acoustic excitation with a speaker, and we were checking how much certain parts of the skeleton move. So that's one example. Here's a matrix of different examples. So this is what we call more of a scanning vibrometer measurement, whether it's the hard, the hard drive with the cover of the hard drive, or a turbine blade, brake rotor and caliper assembly, where there is a direct relationship between the in-plane and out-of-plane component, and the cross-coupling between these two is one of the causes for the brake squealing that I'm sure everyone or most of us have experienced personally. Piezo actuators, piezo sensors, ferroelectric, all that is definitely up and coming field as well. So anytime you want to be able to identify eigen uh, values, eigen vectors, that's where some of these non-contact techniques shine as well. Now, that was more on the macro side. These examples are more on the micro side. I mean, now we are looking at something super tiny. I mean, sometimes it's a couple of hundred microns by a couple of hundred microns in dimensions, and within those we are measuring these. So, for example, these are some PMUT arrays here, a MEMS microphone. This was, I believe, about 300 microns in diameter. And some, definitely we are getting into a lot more telecommunication, RF MEMS, super high frequency type applications, but could also, some of the MEMS microphones applications are in the human audible range. So yeah, hopefully these two slides give you an idea of the the sense of size. I mean, we could be looking at something that is several feet or several meters by several meters to something that is a few microns by few microns. And this is, I hope, shows you the length and breadth of applications where a vibrometer would be a good fit. Now we'll get into some specific examples. So for example, this was done using a 3D microsystem analyzer type system. And here, this particular researcher at Marquette University, they wanted to validate a very, very sort of novel temperature sensor that they're designing and they proposed in this paper. And here, the challenge was this super tiny displacement levels, especially in 3D, and they wanted to compare it. They wanted to do a parametric study. So, as you change the power, what is the minimum detectable displacements? And then they also did a comparison with an FE model. So they had a model from ANSYS, and they wanted to compare it with experimental data. So this is a classic case where really nothing else works, because it's just tiny, high frequencies, pure 3D, and real time, with super high resolution. Metamaterials, if you're not familiar, definitely a very active field of research and development currently for all kinds of applications, whether it's damping materials to thermal dissipation, to cloaking, all kinds of things. And this is some couple of examples here. For people who don't know, metamaterials are these artificially engineered materials with very specific geometries that give it properties that are not possible in naturally occurring materials. So you can design it for certain what they call band gap materials. So you can either amplify or damp out certain frequencies. And if you are into metamaterials, you should definitely, this is a beautiful time to talk to us, because we have all kinds of new algorithms and using artificial intelligence to tap into how to really create these very, very fine grids, and how to create them very accurately using vibrometry. So that's metamaterials for you. Now going slightly bigger, this is done on, and I'm sure Bella remembers this because this measurement was done on one of the VR headsets she owns, and we wanted to see if the speaker in this VR headset is excited, what happens, how is the vibration being propagated, and then one can also take this a step further. Take this surface normal velocities and do some boundary element work on it as well. This is a very interesting measurement, not just because of the geometry, but what we did is we mounted it on an automatically controlled turntable. So we can move it automatically, and then the system is keeping track of all the grid of points and then stitching it automatically. So this was done for transmission loss calculations, and we did some modal work on this particular sample as well. So this is more closer view, right? I mean, the sensor is also closer to the actual object being measured. Now let's go to the other extreme. In this case, this is for, again, as I said, these are not super exotic applications, but they bring out something specific about vibrometry. So in this case, the ability to measure at super long range distances. So this was on a cable stay bridge. The main goal here is to be able to measure the cable, what they call the cable tension forces, because that gives that has a direct correlation to the structural integrity of the bridge itself. In this measurement, we could get data from as far as 500 meters away without any kind of surface preparation and nothing at all. The bottom left photo is this particular sensor has a built-in video camera as well, so you can see exactly where you're pointing, where you're measuring at. So this was a very seemingly challenging measurement for any other sensor, but fairly straightforward for vibrometry type measurement. People also measure drop. So these are two different measurements. These are more would fall under impact type testing, whether it's a drop test or a drop weight test. So a drop test is, you're actually dropping the component itself. With the drop weight test, you're dropping the weight on the component, sort of. But yeah, these are also, if the laser beam is focused to the right position, then you can again do these kinds of measurements as well with a vibrometer. The reason a vibrometer could be a good fit for something like this is because of the high impact velocities, and sometimes those are very challenging for conventional sensors. Now let's look at the next two slides are about measuring through transparent media. So measurement in a vacuum chamber or any environmentally stable uh, container or chamber, whether it's super high temperature, vacuum, high pressure. These are the cases where the ability to go through any transparent media is extremely powerful, because here again, I mean, one of the last measurements we did last year was in a cryo chamber, so super low temperatures where hardly anything else works. So you have to be able to go from outside looking in and make these measurements. So this was measurement through glass. Now, this is a measurement, frankly, I did this in my kitchen just to show measurement on glass. And here, the, the wine glass mode is being excited. And you can see that we are focused. It's 623 hertz is what I was exciting. And here, again, we are not measuring through glass, we are measuring on glass now. So it's all about the beauty of variable focus optics. So depending on where we focus the laser beam, we can pick up the excitation from there. In this measurement, you can see we use this vibrometer called a VibroGo that has a built-in data recorder. So it has a data acquisition sort of built in. So yeah, hopefully this shows you two different examples of measurement through glass, measurement on glass. And the next one is what happens when you don't have direct line of sight. When you cannot see the whole structure in one shot, how do you get to all the different positions? This work by Professor Wei Dong Zhu's group at University of Maryland, they are super creative in using mirrors So they measure something direct and then something through mirrors, and they have algorithms that can stitch the data automatically. They use a very unique way of measuring the scanning vibrometer called CSLDV, which is continuous scanning LDV, where the beam is constantly moving on the surface to pick up various modes. So fascinating research there. But this is still, I would say, structural. So structural meaning lower frequencies. Uh, this is the opposite of lower frequencies. There are vibrometers that can handle all the way to 8 gigahertz. This particular example is on a surface acoustic wave SAW filter. And this particular measurement, you can see this wave propagation. This is almost like a standing wave measurement at 262 megahertz. What we saw in the previous slide was under 2 kilohertz, whereas now we are talking several hundred megahertz in measurement. There are also cases where you need to measure in encapsulated devices. So where the actual device is in there's a silicon layer and the actual device sits inside the layer. So there you cannot, if you move the layer, if you take the layer off, then you are definitely affecting the dynamics of the structure. So you need to be able to have something that is optically transparent to to this SI layer, basically, and these are called broadly called capped MEMS. And here again, we had a couple of examples through SI capped MEMS as well, in cases where you really cannot open up the structure. So this schematic sort of shows how we do it. As long as there's a certain gap between the SI layer and where your MEM structure is. We have specially designed vibrometers with IR laser source and IR camera that can handle this. This particular measurement, if I wouldn't tell you, it's hard to tell that this measurement was done through that capped MEMS. So the actual measurement device, this is a MEMS accelerometer that is underneath a silicon cap. And yeah, the data looks just as you would see it in without that top layer on it. When it comes to microsystem analyzers, there are systems, as I mentioned, going all the way to 8 gigahertz now. This particular work was micro resonator by Professor Bave's group at Purdue University, where we did some measurements at 5 plus gigahertz for him. And again, we don't want to get into too much detail here, but there's a very nice publication. If this is something of interest to you, we can point you in the right direction. So yeah, as I said, 8 gigahertz bandwidth, and you see the setup here. And we used some external probes to excite the structure and then capture the different segments of the resonator, and then we also put it together. So these are the different segments, a couple of shots here. Let me see. And then yeah, but then there's one measurement with the whole thing, but at least you get the point. So we covered a lot of stuff in a very short time, going from macro scanning to micro scanning to measurement at a super long range distances to measurement on glass, through glass, using mirrors, very low frequency, very high frequency. So you see all these different, the central theme being, these are all the characteristics that make laser vibrometry almost indispensable. There are not that many other options when it comes to measuring in these kind of applications. So okay, why non-contact? Now we are kind of getting into some more detail about vibrometry itself. So when would you consider, when does someone consider a non-contact vibrometry-based technique? When mass loading is an issue, so even a little bit of a mass shifts your frequencies enough, or introduces damping, something that affects the dynamics of your structure, or if it's super small, through glass, through water, right? Lightweight, very fragile, super hot, super cold, super high frequency measurements. where you need full field, or there's a safety issue too. If we have had applications where it's not safe, or it's very hard to access, these are the cases where vibrometry is definitely the starting point. Now, what can vibrometers measure on? So basically, anything you can see and is moving. That's the two very basic sort of prerequisites, right? There should be visual line of sight, and if you don't have visual line of sight, can you create visual line of sight using mirrors, for example? And how does a vibrometer work? So now let's get into anytime you hear about vibrometry, it's always going to go back to the Doppler effect. It's a laser Doppler vibrometer. So if you look at the dictionary definition of a Doppler shift or Doppler effect, it always talks about the apparent shift in frequency that is a result of the change in distance between the source and the observer. It's always this definition, the source and the observer. So in terms of a vibrometer, what is the source and what is the observer, right? So hopefully the next slide explains this. In this case, the source would be the measurement object, and the observer is going to be the detector, whatever we use. Now we have a laser source, whether it's a laser diode, a laser, gas, like a He-Ne laser or an IR type laser. And we start off by splitting the beam into two. One beam goes directly to the detector, which is the reference arm. The other part goes to the measurement object. Any change in the optical path length causes this shift, which is basically proportional to the Doppler shift. If we can then bring the Doppler shifted signal back to the detector, we can sort of back calculate or sort of back measure the shift, or the Doppler shift, delta F. And then that delta F has a direct relationship to the vibrational velocity V. Lambda is the wavelength. This is fixed based on the laser source we use. And I have a slide comparing the two, which one to use when. We use the visible red at about 633 nanometers, or we get into the IR range at 1550 nanometers. So if you are interested on which one is right for you, we have a nice white paper as well. We'll be happy to share if that's something of interest to you. But yeah, so that gets to there. Before we get into what a vibrometer is, I found this fascinating work that a Dutch meteorologist had done this test back in the day to show what a Doppler shift is, like really show it, how to. So he had a bunch of musicians on a train playing a single note, and as the train moved away, towards and away from the listener, they could feel a shift in the pitch, even though they were playing the same note. So this is a good way to show the Doppler. I cannot imagine the logistics involved in setting up an experiment like this. In this day and age, they probably use an app, but boy, this must have been quite an undertaking to show what a Doppler shift feels like. What do we get when it comes to the output? So vibrometers that we make are very agnostic to the data acquisition. I mean, you could use a standard analog BNC type out that anybody in the electrical or mechanical vibration acoustic side of things would understand. Is an oscilloscope, an FFT analyzer would work. We also have digital data streams, but in all honesty, you can use whatever works for you. So it's just basically a signal, a voltage in its pure, I guess, in one of the forms. It's just a voltage that is proportional to velocity or displacement. So that's one of the questions we get asked, what does it measure, velocity or displacement? And the answer is both. Both those are considered direct quantities, and then acceleration is the derived quantity when it comes to vibrometry. Okay, so with that, some information on what kind of surfaces. We sort of went through this, so it could be what we optically call specular surfaces, mirror-like surfaces, engineered surfaces. A large size of the pie kind of falls under the engineered surfaces. We have been getting into a lot more bio type surfaces now, skin type surfaces, and those two. There was a time when these were considered the most challenging surfaces, but with the latest technology, this is no different than any other surface. Very fragile, translucent surfaces, those are also another one. And tiny components, that's another one that kind of falls under the umbrella of vibrometry. A quick look at the types of vibrometers, and this is what you will see in terms of breakdown, and out of plane. So there, basically, we are measuring, and this is probably, I would call, the most commonly used vibrometer, where you're measuring the component of the vibration in the direction of the laser beam. There's the out of plane, and then there are flavors of this out of plane, whether it's at single point or it's scanning. And then we get into 3D scanning, and then there are applications where now scanning is also there. Scanning falls under what we call full field, so it's not just one point, but the whole, that there's a whole surface that you're trying to measure. Then there are some special application vibrometers like differential. So you're trying to identify the phase difference between two locations. Rotational vibration. So instead of, for example, meters per second, now you're measuring, radians per second, degrees per second, or degrees, that sort of measurement. Um, Again, there are special webinars, and there's tons of information about products on our website. So we are not going to get into products here. That's not the goal of this webinar. It's more about just introduction to vibrometry. But this is what some of the vibrometers look like, whether it's single point, you know, uh, that you see here. All these are what we call single point vibrometers, designed for different applications, or scanning vibrometers, which is 1D scanning, 3D scanning. And if you ever are in one of our labs, you will also see a robot mounted 3D scanning vibrometer setup for some, speeding up measurements for complex geometries. So 1D scanning, 3D scanning, and all this would what we'll call full field. How does a scanning work? You hear this word a lot, scanning LDV. So fundamentally, what we describe it is what it's called is sequential scanning algorithm. So you define a grid of points, and then the software and the hardware take over. It automatically goes to all these different locations to give you a full field map. So you're repeating the excitation, and it's putting together this. It's keeping track of all the phase information, and at the end of the day, it gives you the data that you saw in the previous slides. So in case of a 1D scanning, you're basically measuring this out of plane component. You have one scan head. In case of a 3D scanning, instead of one, now you have three of these, and then again it follows the same procedure. The system is capable of not just following the grid of points that you have defined, but you can also import geometry if you need to, and all kinds of other exotic ways. But you see that in both these cases, we need to be able to repeat excitation. What happens if you cannot repeat an excitation? What if it's a transient event or some nonlinear event, or just one time shot, right? Shock response or impact, For those cases, we have what's called a multi-point vibrometer, where you have multiple single-point vibrometers looking at the surface in one shot. So here you see a couple of examples: a golf club, a symbol, and a painting here. We have done quite some work in with paintings, which you see here. This was the work done at Museum of Modern Arts. This is one of the Georgia O'Keeffe paintings. If you've not been to Georgia O'Keeffe Museum in Santa Fe, highly recommend it to go there. And as we start getting into much higher, now these becomes more specialized systems. There are applications in super high frequency applications. So all this up to now, what you saw is more lower frequencies, but then this is what high frequency vibrometers look like. There are webinars designed around these systems. So definitely not to go into detail, but just wanted to give you some view as to what these systems look like. There's microscope-based systems with built-in camera. This is what's called a more of an out of plane system, and this is out of plane and in plane system. I had mentioned that I'll have a slide on like what laser source is right for me, so what in what cases would I use a visible, in what cases IR is just fine. So anytime so every time if you have ample return signal coming, so if you are measuring on a very nice surface, then the red is always going to be better, especially because it's now there is QTech everywhere. QTech is the fundamental, the next generation of vibrometry that doesn't care for any kind of surface preparation, nothing. The benefit of the red laser is that because it's the shorter wavelength of the two, it will always give you the finest, the smallest spot diameter possible. And most importantly, if you're making measurements underwater, definitely it will not get absorbed, whereas IR gets absorbed very on the surface or a couple of, very fast underwater. So in that case, you really, so underwater measurements, hands down, visible laser. IR is also very powerful because it is very forgiving to all kinds of different surfaces. So if you are not sure what kind of surfaces you may be dealing with, or if you know that they're going to be challenging or a very steep angle, those are the cases where you want to go with IR. So where there's more uncertainty, you want the flexibility to measure on anything and everything, IR is a better choice. But if you know very specifically what you are getting into, then red. If so, in other words, if red works, red is always choice number one. If red doesn't, then you consider the IR. That's my take on it. Okay. Now, as we approach the last couple of slides, this is another question we get asked. How do I get access to these systems, right? Like, I mean, so I just wanted to point out that there are many different ways to access our systems. If you go on our website, you will see PolyFlex is our term for to each their own, sort of. If you just need some measurements, we have a dedicated team of applications engineers that do nothing but bring in the subject matter expertise and make the measurements for you. If you know how to use the system, or just need some couple of days of training and then you take over, then you can do PolyRent. And then we also have all kinds of leasing options as well. And then of course there's always capital purchase, but sometimes there's this misconception that I have to buy this. It's not for everyone. It's not everybody needs it, frankly. So there are all kinds of options that you can consider. With that, I'll wrap up the structured part of the presentation and see what else we have in terms of questions.
Perfect. Thank you, Vikrant, for your presentation. And now we'll start the Q&A session. And again, you may enter questions in the Q&A box, and as well if you can see the chat box. So let's see. The first question I have here is, what is the minimum and maximum frequency and amplitude a vibrometer system can handle?
So we have customers and applications going all the way from DC to 8 gigahertz, and we have people asking for higher now. So it could be micro positioning stages, nano positioning stages, which is like DC or quasi DC. And yeah, the high end is 8 gigahertz for now.
Thank you, Vikrant. Another question I see here, is there direct Polytec support for PolyFlex in China and South Korea?
Definitely reach out to our local support, local team there. They should be able to guide you with regards to options beyond the CapEx purchase. Yeah.
Thank you. Next question I
PolyFlex
see.
is a global program. So yeah, absolutely. There's some flavor of it in every region. Yeah.
Thank you, Vikrant. Here I see, is it possible to take measurements on a rotating hollow shaft that is also translating? The specific application is a drilling machine.
So there is linear motion and then there is rotational as well. Yeah, we actually have some machining applications, some manufacturing folks using these vibrometers for that. Um, QTech has been very successful in those kinds of measurements. Yes, they are tricky because a vibrometer is fundamentally, if you go back to the basics of interferometry, you are measuring the component in the direction of the laser beam. Now, when you're making this measurement in this particular attendee's case, there is always motion perpendicular to the laser beam. So it's going to add noise to the data. So, but we can we can almost like theoretically calculate what the noise floor will be based on the RPM. So we can take a very good guess as to what would be the probability of success of a measurement like this. But now we have absolutely done these measurements, especially with the QTech technology. It is it is very robust in the sense that it is designed to reduce the effect of these signal dropouts. The dropouts happen because of this motion perpendicular to the laser beam. Yeah, the alignment and everything has to be paid special attention to, but yeah, definitely worth talking about. I won't say absolutely not. So
Thank you, Vikram. The next question I have here is, can I use QTech and Hini with one set of electronics?
so the new scanning LDVs, the VibroScan series, is actually a QTech Hini. So absolutely, all our VibroScan series, we have almost like done best of both worlds with that. We have, you know, in the past, the QTech technology was applied only to IR, but everything is QTech with the VibroScan now. So absolutely.
Thank you. The next question I have is, the rent and lease program available in the US? Can the rental payment be considered for the purchase?
Yeah, so please reach out to us. We have special programs and policies in place. So for example, yeah, once we find out, for example, if it's a lease, what we would ask you is what you're looking at, of course, what system, what kind of lease terms would you like? Some people like1 year to 3 years with a certain down, so if we know a little more, we basically, what we do is we tailor a lease based on your needs.
Vikram, I have a little bit harder time hearing you. It says poor network connection. I'm not sure if your attendees have the same problem, but we'll see as we go along. I'll ask the next question and hopefully it works.
I'm sorry, can you hear me, Bella? Yeah, I can
Now,
hear you okay now.
okay, now it
Yeah,
works
I feel
much
like I
better.
lost you for a couple of, yeah, yeah.
Okay, perfect. Okay, next question I have here. How is structured displacement characterized, which is excited with a frequency sweep, not a single frequency? What are the possible sources of errors in displacements, measurements, and or calculation from velocity information in the sweep scenario?
Hmm. Sweep measurement, yeah, frankly, it's no different than a chirp or more broadband. So there are two types of broadband excitations, I guess. So very broadly speaking, one is like where you're putting all frequencies at once. So like a periodic chirp or a white noise or a burst random or a pseudo random. Or there is the sweep where you're going one frequency at a time. So you're putting all your energy in that one bin. And frankly, it's just about the data acquisition side of things, right? So if you have your own data acquisition and you're doing a sweep, Um, you would use peak hold for averaging, because then that's going to always take the highest in a particular bin. Audio and hearing applications, they absolutely prefer sweep over chirp. So yeah, if you're using your own data acquisition system, that's how I would say, you just do it like, you just basically record the time domain, and then you can do all kinds of things these days in within the DAC or in Python or MATLAB, and we have all kinds of plugins for those too. Now the second part of the question was the velocity or displacement. Bella, can you repeat that part?
Let me go back to the second part. One moment. Yes, what are the possible sources of errors in displacement measurement and or calculation from velocity information in the sweep scenario?
Yeah, no, frankly, I don't, nothing special about displacement, because if you are after displacement, then you just go pure displacement. So there is no, so we are not, yeah, I guess this comes from the fact that maybe in the past people used only velocity and integrated velocity to displacement. But if you are after displacement, then I would just start with displacement, so there is no, yeah, if you have like tonal excitation, then you can obviously go velocity to displacement without any error. But if you have broadband, you might as well start with displacement. So that should resolve. So the answer is none, because you are going pure displacement anyway.
Perfect. Thanks, Vikran. Sorry if I butchered some of the words here, but I will try to read question as is. What would you suggest for spring vibration measurement that is perpendicular to the spring? Note spring size is 3 to 6 inches and would be concerned with spring colli curvature.
What a measurement is perpendicular to the spring? So I'm guessing if I'm looking at a spring, it's kind of in and out. If I have a spring in, I apologize if I'm completely misunderstanding this. Um, if the whole thing is moving, then you're going to fall off the spring itself. So honestly, it's not a good one, right? I mean, um, if you fall off, if you are not on the surface of the spring, yeah, then you're going to get bits and pieces, right? You're going to get a little bit, and then you're going to not see anything. It's going to be noise. So I don't know, maybe it's not a good one, because if, I mean, think about it this way, if you take a laser vibrometer, or, well, let's simplify it, a laser pointer, and if the point doesn't stay on the spring, then you're not going to measure it. Yeah, I mean, yeah, unless your motion is small enough that the laser beam never falls off the spring, then yeah, then there are ways. But if it's falling off, then yeah, there's just, yeah, there's nothing much we can do, sorry. That's yeah, unless I'm misunderstanding, then please reach out and we can discuss in more detail.
Thanks, Vikran. This one I think is a follow-up from the rotating shaft one. What if the rotating shaft is a hexagonal cross-section?
Hmm. um that's an interesting question, because it doesn't so it's almost like vibrometer doesn't care about the it doesn't care about the absolute distance. So in other words, what I mean is, let's say I'm measuring on a wall, and the wall is moving at let's say 100 hertz, um, at 6 microns. It doesn't that I'm going to measure 100 hertz, 6 microns, whether I am a meter from the wall or I am 5 meters from the wall. That measurement is not going to change. It doesn't care about this absolute standoff distance. So now, if you think about that concept and take it to a hexagonal shaft, if it's not cylindrical, that distance is changing, but a vibrometer really doesn't care. In this case, in the rotational measurement, the more critical component is going to be the noise floor. how can we mitigate, how can we minimize the noise that is being introduced because of the rotation of the shaft. That is going to be more critical than the shape of the shaft. And for the shape, definitely look at the rotational vibrometer as well, because maybe what you are after is both, or the degrees per second, or degrees, and the radial motion. So
Thank you. Next question that we have here, is there any autofocus function of the laser beam? We have an old system and it requires manual adjustments.
yeah, no, definitely reach out to us. The systems. We still have maybe one model that has a manual focus, but everything else is autofocus now. So both in terms of, I mean, all the scanning vibrometers are always autofocus, but I would say, barring one system, everything is autofocus now. So no, definitely that has changed a lot.
Thank you, Vikran. And I'll do again a follow up on the rotating shaft.
Yep, yep.
Is the noise floor frequency dependent?
Frequency, yeah, because it's RPM dependent. So the depending on the RPM, yeah, you'll definitely see the noise floor change.
Perfect. Thank you. Next question. Hello, thanks for the talk. Can we also measure vibroacoustic materials? If we have a structure inside the aquarium and we excite it with microphone, can LDV measure the response of materials under excitation? If yes, how accurate is it? Thanks.
Vibroacoustics of, I mean, frankly, am I understanding this right? They're asking about measurement inside water.
Inside the aquarium, yeah, it looks like it.
Yeah,
I would
yeah. In
assume
fact,
that
we have
there's
some
water.
really nice papers too. Um, yeah. I mean, so the difference between measuring in air and in water, frankly, is a vibrometer doesn't care. It doesn't know what it's measuring. So the accuracy doesn't change. What changes is the noise floor, obviously, right? Depending on what we are measuring, how we are getting there, what's the clarity of the water. So the vibrometer is always going to give you a reading, right? But we what we have to do, if you're after absolute amplitudes, then you just have to compensate for the refractive index change, right? So in air, basically you take the value of the velocity. Let's say it's 1 micron per second. It is 1 micron per second. If you are going through water, then you divide the 1 micron, whatever the vibrometer reads, by the refractive index of the medium, right? So 1.3, whatever that is, right? And that gives you the pure absolute velocity number. Frequency doesn't change. It doesn't. Yeah, the frequency. If there's something at 500 hertz, you're still going to see it at 500 hertz. So if there's some sensor exciting your structure, yeah, so that's the only thing. So it depends what you are after. If you are after frequency, then doesn't matter. If you're after pure, like, let's say, attenuation, depending on certain treatments, then you may absolutely want to do the, and now again, if it's A to B comparison, then it doesn't matter, right? What I mean is, like, yeah, but one is going to be off by X, the other one is also going to be off by X, right? So it depends whether you want to go absolute, then you have to compensate for the refractive index. And if not, then yeah, then you can just do A to B comparison. If this is of interest to you, we have a couple of nice, and Bella, if this person needs it, I think we have a nice application note on measurement through water, through transparent media.
Yeah, please reach out and we will email that to you. And the same attendee has another question, which it says, does Polytec have used LDV for sale for educational purposes? I'm guessing to sell for educational purposes.
Yes, no, please reach out. Yeah, every once in a while, Bella is the one who drives these projects many times. But yeah, please let us know. I mean, we'll be happy to talk. It kind of comes and goes. So I mean, we try our best to accommodate, where we can with our demo systems. And yeah, our demo systems are well maintained. It just depends what you want. So it's very hard to tell yes or no, but just because we don't know what you need. But once we find out, we can see if we have something to offer.
Perfect. And the attendee says, sure, that's going to help. I will reach out. Definitely. Many thanks. So,
Thank you.
okay, next question here. Do you have any advice or methods on how you can decouple vibrations from the laser source or mechanical setup of the laser vibrometer from the measurement target under test?
Excellent question. I like this one. um yeah, so like, what I think, let me see if I can rephrase it. Like, what if the how do you ensure that the vibration of the vibrometer is not affecting the data? And there are a couple of ways to look at this. Number one, yes, if you go back to the schematic of an interferometer, the vibrometer doesn't know the difference whether the structure under interest is moving or the vibrometer is moving. So it doesn't know it. It's gonna consider both as the same, whether the vibrometer moves or the structure moves. So what do we do? So a couple of things to keep in mind. Number one, frequency of interest. If you're the Anytime you mount a vibrometer on a tripod or suspend it somewhere, those are super low frequencies. So I mean, we are talking sub 2, 3, 5 hertz, right? It cannot move much faster than that. So it depends on the frequency of interest, right? So if your structure is moving at 500 hertz, and the vibrometer, if you are just really worried about it, you just apply a 10 hertz high pass. It gets rid of all that stuff. Now, what if the vibrometer is moving in the same frequency range as your frequency of interest? Now we have to do something. So there are all kinds of tips and tricks that we can play with. So for example, number one, we can do a background measurement, just like how you would do if you're doing a microphone, SPL measurement. We also have, in some of our sensors, or you can always mount it. You can also mount a contact transducer on the back of a vibrometer and normalize your data. So we have done that, honestly, not that many times in my 20 years, but maybe a couple of times, mounting like an accelerometer, some kind of contact seismic sense, some kind of sensor on the back of the vibrometer, and then measuring that, and then removing the movement of the vibrometer from the data. So again, we have some nice material on that as well. Again, not a very common problem, but definitely there are ways. Like, let's say the whole foundation is moving. How do you get rid of that stuff? Again, only matters if it's in the frequency of interest, of your what you are interested in, right? So
Thank you, Vikrant. We're almost out of time. I'll try to get to these. Okay, the other attendees said really helpful. Thank you. So appreciate it. Try to hurry up with the last question or two. We'll
Mhm.
see how much time. This one is, do remote testing services have an NDA?
If you I mean, totally depends on the end customer. We definitely so regardless of whether we have an NDA or not, unless the work is published, it never shows up anywhere. So we respect that component with or without an NDA. But with many customers, yeah, we either provide our template and then the customer reviews it, or we use a customer's NDA template and we review it, and then once it is fully executed, then we can talk even more freely. So, but yeah, both options are fine. Yeah, I mean, we are. I think, I mean, not a week goes by when the president doesn't have a few NDAs on his desk to sign from HR. So it's fairly common for us.
Perfect, Vikrant. This is the last question we will answer today. How much physical area can the scanning 1D vibrometer detect per sample? Is there some calculator?
Mm. So first of all, here's the good news: you don't even need to do it yourself. So as soon as you start, it's part of the process itself. So The software does this calculation for you, so you don't need to worry about it. So, but let's go back to the basics. The scanning vibrometer has two mirrors, the X mirror and the Y mirror. So this is the X mirror is plus minus 25 degrees, so 50 degrees total. The Y mirror is plus minus 40 degrees. So, sorry, plus minus 20 degrees, so 40 degrees total. So 50 and 40 in the Y. So you can imagine that the farther away you are from the sample, the more area you can cover, right? The closer you are, the smaller the area, right? Because the cone effect. So, but as soon as you do because there's a live video camera with the scanning LDV. So as soon as you do this 2D alignment step, and as soon as you're done with that step, automatically the system will show you this hashed area where it shows you exactly what is your field of view for that standoff distance. So yes, you can do the math based on these 40 degrees and 50 degrees, but also you don't need to. The software is smart enough to tell you that, hey, don't put points to the left of this hash. We cannot reach it, in this particular standoff. If you do need to reach it, back off, go back some, So it's smart enough to do the thinking, I guess, the smarts for you.
Great. I mean, first of all, we want to thank attendees for all the great questions and interesting
Yeah,
questions. So
very nice.
definitely. And then thank you, Vikrant, for answering all of them. And yeah, this brings us to the end of today's webinar. We would like to thank everyone for attending, and we're looking forward to welcoming you again to our other webinars and events. Thank you for your attention and have a great day.
Thank you.